The theme for today is complex exponentials, right? So we start with complex numbers. I gave you a small warm-up so that you could remember how complex numbers work. Usually, we represent a complex number as a variable z. It belongs to the set of the complex numbers. And there are two main forms of representation, right? Cartesian coordinates and polar coordinates. And this is an important concept that sometimes is not totally clear for everyone. So we have the complex plane, real and imaginary, and my number z can be anywhere here. Let's say it's here, for instance. So you might remember that if we're using this notation, it means we have A here, B here, right? If we're using this notation, we have a radius, and actually I prefer the symbol omega. Let's stick to this symbol, omega. Okay. So A is real, B is real, JB is imaginary, A plus JB is complex, R is real and positive. It's always positive. If I have another number here, Z2, it will have an omega 2, R2, and it will be positive. It's always positive. And this guy is complex. This guy, we can break it using what? Does anyone remember that?
The Euler identity.
Euler identity. So E, this guy, E to the J omega equals cosine of omega plus J sine of omega. And this is actually part of the way that we can use to convert from one representation to the other. Because here we break this in real and imaginary. Then if we just multiply both parts by R, we come back to A and B. This guy is real and positive. This guy, if we look at this guy only, A to the J omega, what is its absolute value?
1.
It's always 1. The absolute value of Z is R itself. But when I take R off, if I divide Z by R, I get E to the J omega, and it's always 1. Because you might have seen this for the square root of cosine of something squared. Sine of something squared is always 1 if you have the same angle here, because then you're over an unit circle here. So you're just varying the angle with constant absolute value, constant radius 1. And what is the angle of this particular guy, a to the g omega. This guy, a to the j omega, lives here, right? It's in the same direction of z, but with unit radius. So what is its angle? Omega.
Omega.
Omega. So this is a way to represent a complex number of unit radius and angle omega. And this is what makes this representation so useful, because we have radius and angle. And this is algebraically accurate, differently than this representation, which is R angle omega. This is used as well. Maybe you have seen this when you studied phasors. It's a possible representation, but it does not. This guy is a convention. It is not a mathematically sound entity. While this guy is the number E elevated to another number times another number. We have no convention here. It's just some algebraic manipulations of our numbers. So this is a mathematically accurate way of representing angle, because this guy has unit 1 and angle theta. Okay, now for operations with complex numbers. If I have, for instance, Z1 plus Z2 equals Z3. If I give you Z1 and Z2, what is the easiest way to proceed for the summation of them? Using Cartesian or polar coordinates? Cartesian, because then you have Z3 equals A1 plus A2 plus J B1 plus B2. It's quick and straightforward. Then, if I have some Z3 that equals Z1 times Z2, are you still using this representation, or should things be easier here? Both are correct, we know, but where are things easier? Sorry? Polar representation. So what happens to the radius of R3, radius of Z3? R1 times R2, if we have these guys from here. What happens to the angle? Plus omega 2. So here, e to the j omega 1 plus omega 2. So we multiply the radii. We multiply the radii and we sum the angles. That's how we multiply complex number. Of course, we could do this. Z3 equals A1 plus JB1 times B1 plus JB2. Yeah. Then we distribute things. We proceed with the multiplication. We get the same result, but this is easier and faster. So the important point here is that when we multiply complex numbers, we sum the angles and we multiply the radii. Now, exponentiation is composed of multiplications. For instance, now let's go to the exponentiation. Say we have some z that equals 2 times e to the j. Let's go with 15 degrees. 15 degrees in radians. That's 90 is pi over 2. Then we have 90 divided by 6 is 15, right? Yes. So divide by 2 by 6, pi divided by 12. This is a number with radius 2 and angle 15 degrees. Let's represent it here. Let's say the unit circle is here. So our guy is somewhere around here, z. Our omega is j over pi, j. Our omega is pi divided by 12. Radius 2. What happens if I square it? We're starting to do exponentiation. What happens here? What's the radius of z squared? 4. The angle is pi over 6. Then if I cube it, I hope this verb does exist. If I cube it, I have how much as radius? 8. And the angle is pi over 4, which is pi over 12 times 3. So what happens is that I elevate the radius to this exponent and I multiply the angle by the exponent, right? At this moment, we're working with integer exponents. And we're doing that now because we're starting with discrete signals, discrete exponentials. So we'll define them only for integer instance of time. So I will open now a Google Colab, discrete exponentials. Part of the script is ready. We just have to define n. Let's go with n and p.a range 0 and 1. Let's start with not many numbers. Z, we need a z. Our z is that one. Is z equals 2 times np dot x 1j times np dot pi over 12, 15 degrees. Now our z of n will be, that's right, z to the power of n. What's happening here? Control F9, so we run all the cells. Okay, so here I have z to the 0, which is 1. Anything to the 0 is 1. 1, purely real. Now I have z here. This is our z, which has radius 2, angle 15 degrees. So if I go on here with z to the power of 2, I will have something like here, right? Let's go, one more. Now z squared. So this guy has twice the angle of this guy, and it has the radius of this guy squared. Now we can go on to 10. Out of scale. So 10 times, we have 15 degrees, 150 degrees, right? This last guy has 150 degrees, and its radius is very large. Is actually, I'm going, if I want to see 10 as the last instance, I need 11. Now, this guy has 150 degrees, and its radius is 2 to the power of 10, which is 512, right? $1,024? 2 to the power, yes, sure. Thank you. 1,024. I was misguided by this 500 right here. 2 to the power of 10 is 1,024, which is the radius of this guy. So this guy is growing really quickly, right? What can I do to make it grow slow, in a slower pace? I don't want to change the rate at which the angle changes, only the radius. What should I do? The value of the radius, right? Closer to 1. So if I have something closer to 1, like 1.1, for instance, then I'm growing up more slowly. We can go further now. We can go to 100. So now, at each value of n, I'm multiplying the radius by 1.1, which is not that much. And I'm summing the angle in the same manner I was doing before. Here below, I have another script where I take all these points and I plot them as a time series. Here I have the real part of z, of the signal z of n, the real part, the imaginary part, the magnitude, and the angle. So with exponentiation, things are more easily interpretable in polar coordinates. So we see the radius growing up linearly. When it reaches pi, it goes to minus pi. So we have this, we call this phase wrapping of the angle, because it is growing linearly, but we have the modulo pi operation. And here we can clearly see an exponential. So we have exponential growth. What should I do to have exponential decay instead of growth? If my radius is less than 1, for instance, 0.99, then I'm going inside. I'm converging to the center. So here's my exponential decay. Nothing changes with the angle. And here, real and imaginary parts of the function. So that's how exponential functions work. So the radius amounts for rate of decay or rate of growth. What happens if I increase omega? If I increase this guy, I keep the radius, but I use a larger omega. Do I have any change here in this graph? Here, it will grow more steeply, right, with a larger inclination. The frequency here will also be larger. Actually, this guy, this omega, in the context of discrete exponentials, is called a frequency. This works better. So it's a normalized frequency. What's the unit that I should use here? This guy is an angle, right? Radians. In principle, if this is just a number, this is radians. When I put it inside a function, z to the n, each time I increase n by 1 unit, I increase the angle of the result by omega radians. So this guy is radians per sample. This is why it's normalized. It's radians per sample. So if I know the sampling frequency and I multiply this by sampling frequency, I have radius per sample times samples per second, sampling frequency or sampling rate. Here I have radians per second. If I multiply it by the sampling frequency. Then if I multiply it by 2 pi, or divide by 2 pi. I am at radians per second. I want to go to hertz. I need to divide by 2 pi. Then I get hertz. Okay, so we have 15 here in our example. Suppose we have a sampling rate or sampling frequency of 1,000 samples per second, which is 1,000 hertz. So we are at 15 times 1,000 radians per second. If we divide this by 2 pi, we get the real frequency in hertz. So this guy is frequency. If I increase it, I will increase the frequency of oscillation of these two components here. Divided by 9, for instance. Slightly larger frequency. If I go 0.1 times this, and here if I go 0.5, now things are interesting. 0.5 is 90 degrees, 0.5 times 2 pi, 90 degrees. So always an increase of 90. So that's too much. 0.4, what do we have? A pentagon. 0.2. Okay, so I guess you're convinced that this is the frequency of exponentials. And why are we talking about exponentials, exponential functions and defining them very carefully? Because we will take arbitrary signals and break them into exponentials. And in the discrete case, the exponentials will follow this this notation. All of them will be z to the n. So we have a bunch of z to the n's to represent any discrete signal. So next topic, another interesting one. Let's go with the small, relatively small frequency. Control F9. Okay. So 0.1 is a small frequency, right? Let's call this a small frequency. We've seen that 0.4 is a very high frequency for our standards because you can no longer recognize the sines and cosines very easily. So let's go back to 0.1. If 0.1 is a low frequency and 0.4 is a high frequency, what do you think will be 2.1? Same as 0.1, actually. Control F9. Same as 0.1. Why? Let's do some algebra. So we have blue. Where's the blue? Here. We have e to the j some omega plus 2 pi. That's what I did, because I had something times 2 pi, and I added 2 to it. So I'm adding 2 pi to the frequency times n. we can separate this as a to the j omega n times e to the j 2 pi n. So e to the j 2 pi n. What's the radius of this number here? 1. And its angle, so we have the unit circle here. It's somewhere here. The angle is 2 pi times n. So 1 pi, 2 pi, I come back here, times n, I always come back here. So this guy is the real number 1. So that's it. E to the j omega plus 2 pi n equals e to the j omega n. This works too with sine and cosine. You can demonstrate that the cosine of omega plus 2 pi n equals the cosine of omega n, and same for sine. I have another script here which gives some visual intuition for this. Frequency, non-unicity. Here's my script. We start with false. And what this script does is it creates a cosine and it samples the cosine. This is the sampled signal. This is what the continuous signal would look like. Of course, this is also discrete, just with a finer discretization. But let's pretend it's cosine of omega t. What this function does is, if I put true here, it plots with my frequency, omega, and also with omega plus 2 pi. This is just to show you that if I add 2 pi with, doesn't matter which frequency, I get the same discrete signal, the same discrete signal. So we never know which was the original frequency when we have a sinusoid, a cosine or a sine. And that's also an issue when we use Fourier decomposition, because we decompose in exponentials. I did this here earlier, right? X of n equals a sum of many z of n's with some coefficients here. So we assume they are the lowest possible frequency among all possibilities of multiples of 2 pi. But they can be anything. We can go further here. It's already here, it's commented. Plus 4 pi. Different continuous signal, exactly the same discrete signal, because it will sample the continuous signal exactly where the 3, in this case, cosines meet. I'm plotting here the example for a cosine. This extends, of course, to sine, and consequently to complex exponentials with unit radius, right? Complex exponentials with unit radius, because they're composed of cosines and sines. So that's it about the non-unicity. absolute summability is the next concept. Let's try to be quick. So we've seen that what dictates the frequency of oscillation of my exponentials is this guy, omega. Let's go again. Z to the n equals R e to the j omega to the n. So what dictates frequency is this guy. What dictates rate of growth or decay is this guy. So what's absolute summability? It's something that we define for both continuous and discrete signals, which will be useful to define the Fourier transforms. It will be useful to define which signals admit a Fourier representation, and it will be useful if you're working with control systems to define whether a system is stable or unstable. So we define a sum n from minus infinity to plus infinity of my signal, x of n, absolute, so it's the absolute value. That's it. Okay. X of n times a heavy side step. So you remember this guy, right? U of n, U of n. I have here 0 and here 1.
The camera is not recording the top side of the whiteboard.
Let's check it. Okay now?
Yeah, but also this OBS window is overlapping the whiteboard.
Yes. Let's try this.
Okay.
That shouldn't be happening. Okay. Sorry? It's this one, actually. It's the whole screen. Okay, thank you, Khalid. If this absolute sum of the right side of the signal is finite, we call this an absolutely summable signal. So when does that happen? What's the condition that I should meet in order to have this sum of the absolute values of all elements of my discrete signal for non-negative time? For this sum to converge, what do you think?
Maybe they have to be band limited signals.
Sorry, I couldn't understand you.
Band limited signals, maybe.
Time limited signals.
Yeah.
But we're only allowed to define signals of this type. All of our signals are exponentials. So
So
for a
they
time
have to have a. Oh, sorry. I was going to say maybe a radius. Okay, never mind.
let's go to the other um, script and praying for my computer not to shut down. Control F9. Do you think this guy is absolutely summable? Yes,
Yes.
because the amplitude is decreasing. Eventually, it will be too small to add something. Uh, the amplitude tends to zero when n tends to infinity. So the sum will converge. Why is this exponential function decreasing? Because the radius is smaller than 1. So for this to be true, I need r smaller than 1. R is the absolute value of z, right? R is the absolute value of z. So we need this, the absolute value of z to be smaller than 1. So if we're here in the complex plane of all possible z's, real part of z, imaginary part of z, what's the region of z's where this criterion is met? Criterion. We
The
can
unit
define
circle
a unit circle.
without the
We have
board.
1 minus 1 minus j. For any z here, we have a decreasing exponential. It doesn't matter the angle. The angle, we just set the frequency. If the angle is 0, I have a purely real exponential. So when the angle is 0, let's go with this. Purely real, right? Only real. And here, nothing in the imaginary part. The phase is always 0. If I have pi, np dot pi, I have a negative number, right? Negative number is somewhere here. So I'm always just changing the sign. What is happening here? Ah, okay, pi, no, just this. So alternating sign, positive, negative. What's this? Whatever it is multiplied by 10 to the minus 15. So it's 0. So we have a purely real signal here. This is just numerical residual, purely real. The phase here alternates between 0 and pi, positive and negative. Okay. So this is the region of convergence of this kind of signal. That's it for complex discrete exponentials, I guess. Let me check. If
But it does not include the boundary, right? The circle boundary.
yes, the boundary is not included. It's smaller than 1, not less or equal to. Because if I have R equals 1, then I have 1, terrible. Then I have 1 e to the j omega to n. So this will always be 1. The absolute value will always be 1. So I'm summing 1 plus 1 plus 1 plus 1 plus 1. Okay, it's well behaved. It's bounded. It doesn't go up to infinity if I see each sample individually, but the sum sums up to infinity. So it's less than, not less than or equal to. Now we go to, there's one important thing here. What happens when I multiply a discrete exponential function by some exponential constant? So I have x of n equals r e to the j omega. And what happens if I have some constant scalar complex number and I multiply it by x of n? What happens is j omega n. If I take each sample individually, I have to sum the phase of this guy, and I have to multiply the radius of this guy by the radius of the original signal. So let's try to draw an interesting example here. Point 1 and p dot pi. This is our function. Notice that this is the cosine part, so it starts at 1, and this is the sine part, it starts at 0, just like cosine and sine are expected to behave. Now I will multiply the whole function by some constant. Say 2 times np dot exp j 45 degrees. 1j 45 is pi by 4, right? So we're adding the phase to each number. So instead of starting at phase 0 here for n equals to 0, I'm starting with pi over 4. So I no longer have a pure cosine and a pure sine. Pure cosine and pure sine. So for them to be really pure, I need 1. Here. So I'm adding phase. And this is the phase I've just added. I have here cosine of omega n plus 45 degrees. And here I have the sine of omega n plus 45 degrees. So if we represent C as, okay, we can say, we can use this representation. Radius, e to the j angle of C. So this amounts to absolute value of C times R e to the j omega n plus the angle of C. If I break this into sine and cosine with the Euler's formula, we have absolute value of C cosine of omega n plus angle of C plus absolute value of C, j sine of omega n plus angle of C. So multiplying by a complex number causes this. You shift the sines and cosines, and the phase that is the phase at which they're being shifted is exactly the phase of the number. This is what you do with phasors, right? You have a circuit, you represent the input as a phasor, and the impedance of the circuit as another phasor, another complex number. So you have, as a result, a third complex number, and the phase of this complex number will be the phase of your sine or cosine, depending on your input.
You're assuming the R is equal to 0?
Ah, thank you very much. Times R, times R. No, I was not assuming, I was just missing it. So keep in mind that multiplying by a complex number causes increase or decrease of the amplitudes according to the radius of the complex number, and causes phase in the sines and cosines. Now, let's go with the 0.9. Here too, instead of starting at unit amplitude for this guy, for the envelope of the exponential, I'm starting with 2, which is the absolute value of my number. Right, now we have to comment on some activities. Guess the parameters of a discrete complex exponential. This is what I'm asking you to do after this class. Discrete exponential. How does it work? You download the data. I'm using the very useful GDown package here. So I'm downloading from my Google Drive. You will download a sequence. You will visualize the sequence. Here it is. Real part, imaginary part. What can we say already about this sequence? About it's z to the n. What can we say about z?
Well, the radius is less than 1.
The radius is smaller than 1. That's one thing we can assure. Guess the parameters. Guess what's z. That's it. I think I've put an example here where I try r equals to 1.01 and omega equals to 0.2. And then
Can we, like, instead of just trying randomly, can we just use some additional processing to estimate the radius in omega?
yes, you can. You can do it by trial and error or use any method you like.
Okay.
If you're doing only trial and error, you edit only here. If you want to use some other method, you can try. But I suggest you to try to do it with trial and error just to strengthen the intuition of which of these two components mean in the composition of the signal. Okay, then when you think that things are sufficiently similar here, you're done. You save it and you post it as your answer here.